let's look at this thing called simple harmonic motion. It's called simple not necessarily because it's easy. Yeah, it is easy. But it's the motion itself. It's very simple motion. Harmonic because it's going backwards and forwards. It has harmony to it. And this is simple harmonic motion. So a particle simply moves backwards and forwards in such a way that at any point in time, its acceleration is directly proportional to its displacement. Voila. Acceleration proportional to displacement. Well, if that's true, it's got to be equal to some constant times displacement. But more than just any constant, it needs to be a negative constant for it to work. So rather than just writing k, we write minus n squared, and that forces the constant to be a negative number. So that's it. If they tell me simple harmonic motion, then that's what I know. And that's my differential equation that I then go and work with. All right, let's try and create all of the other things for simple harmonic motion. I've got acceleration in terms of displacement, so I'll rewrite acceleration as v to v dx. And I'll separate the variables. Let's come up with some ideas. What do we know about simple harmonic motion? I need some initial condition. In any simple harmonic motion, if we're going backwards and forwards, we know that when it's out at its furthest point, either side, it must stop. So that's something I know. Let's just call it the amplitude. That's as far out we go, amplitude. So I've labelled it A. I know at that point velocity will be 0. Let's now come up with an equation that links velocity and displacement together. So if I integrate both sides, I'll get v squared and then minus n squared x squared on the right hand side. Substituting in, I get this lovely formula. V squared is equal to n squared, a squared minus x squared. Some people say, can we quote this? I'm personally not a fan of quoting it. I don't see the need to because it's very easy to just integrate. Why worry about memorising this formula that I can use for a handful of situations? So velocity therefore is plus or minus n outside of the square root of a squared minus x squared. Now what this does is confirm what we said about simple harmonic motion, because remember, velocity squared has to be greater than or equal to 0, or another way of thinking about it, whatever's under the square root sign must be a positive number. And if I was to solve that little quadratic equation, I get that x is in between minus a and a. And that's what we know simple harmonic motion to do. It goes backwards and forwards between a and minus a. Well, let's now try and find something that links displacement and time together. So I'll now call velocity dx to t. I've got to choose whether I'm going to take positive square root or negative square root. I've gone with negative. And the reason why? The initial conditions that I am using is that at the amplitude, velocity is equal to 0. So it's like I'm starting at the amplitude, if you like. Well, if that's true, if I want to model this, I know I'm going to either get a sine curve or a cosine curve. And they're the same curve at the end of the day, just with some shift happening. So I want to pick the one that best models what I got. So if I'm starting at the amplitude, the best model I've got is a cosine curve, because a cosine curve starts at the amplitude. That's why I chose negative, because when I turn it upside down so I can do my integration, we get minus 1 on the square root of a squared minus x squared, which is our standard integral for inverse cos. If I had started at the centre of motion, then I would have picked the positive. And then that would use the sine curve, because then the sine curve models it better. All right, let's actually do our integration then. And there it is, we get our inverse cos. So t is 1 on n, the inverse cos of x on a, going from a to x. It just makes the maths nicer doing it that way. I could have chosen inverse sine and gone with the positive. But then I would, instead of having a nice neat angle of x on a, I would have x on a with some sort of shift happening as well, and just, why make things hard for myself? Right, substitute in, and we end up with 1 on n inverse cos of x on a, but that's t. We want to make x the subject, so multiply by the n, undo the inverse cos, and there it is. It's a nice cosine function. X is equal to a cos nt. So in general, what do we know? We know that acceleration is minus n squared x. It's quite okay to quote that if they tell me it's simple harmonic motion. Sometimes they'll ask me to prove it. To prove it's in simple harmonic motion. V squared equals n squared, a squared minus x squared. You notice I haven't boxed that one because, as I say, it's not one I bother to really memorise and use. I just let the calculus do the work for me. But that would allow you to find the path of the particle. X equals A cos nt, or A sin nt, depending on which model you've chosen. You notice I have boxed that one. It is okay to quote that for simple harmonic motion. It just depends on what sort of problem. Do I start with the trig curve or do I start with the acceleration? And the question, I guess, dictates which way I'll go. We know the particle has a period. It's a cosine or a sine curve. Period of a trig curve, 2 pi on n. That's exactly the same as our trig. Then there's this thing called frequency, and frequency is just the reciprocal of the period. Because period tells you how long it takes for one complete oscillation, whereas frequency tells you how many oscillations there are in a particular time period. Yeah, usually seconds for what we're looking at, but it doesn't have to be seconds, it's whatever the time units happen to be. So here's one where they've given us the displacement. It's x equals 4 sine 3t, and they want us to show it's in simple harmonic motion. So we need to show that law, if you like. Acceleration is equal to some negative constant times the displacement. So I'll just differentiate it twice with respect to time. It's just a straight trig differentiation. I get minus 36 sine 3t. Well, yeah, that's minus 9x. So it is in simple harmonic motion. Probably not bad to say because it satisfies minus n squared x or that sort of thing, but I've proven it or shown it. It did say find the period, period of a trig curve, 2 pi on 3, but we're talking about motion here, so we've got to put some units on that. So seconds. Although it didn't actually specify the units there, I'm just assuming it's seconds because most of our motion questions using the SI units are seconds and meters and things like that. Find the interval in which the particle moves. Now I'm not going to start with the acceleration one and do all that for this one because I know it's a trig curve. I use my knowledge of trig. So what's the interval? Well, displacement's 4 sine 3t. So that's going in between minus 4 and 4. Just like the trig curve goes between minus 4 and 4. And what's the greatest speed? I can look at the velocity equation. The maximum of that cosine function, or the amplitude, is 12. So the greatest speed would be 12. Interestingly, I said units per second there rather than meters per second. But anyway, this time I'm starting with the acceleration equation. And giving me some initial conditions. We are starting 3 centimeters to the right of the origin. So notice that for this one, I'm not necessarily starting at the center, well, I'm certainly not starting at the center. Am I at the amplitude? Can't really tell here. And I guess the answer is no, because they've told me I'm traveling with a velocity of 6. So I can't be starting at the amplitude either. So find the interval in which the particle moves and the greatest acceleration. V to V dx. Let's see what happens. Separate my variables. They've given me the link of 3 and 6. Integrate. Substitute in. There is my equation for velocity squared. So I want to solve that in equation. I'm in between minus 3 root 2 and 3 root 2 when I solve that. The greatest acceleration. Well, the greatest acceleration is minus n squared x, so the greatest acceleration must happen at the greatest displacement, directly proportional. So it's happening at x equals 3 root 2 or minus 3 root 2, it doesn't really matter. One's a negative acceleration, one's a positive acceleration, but it's just acceleration. So I've said minus 12 root 2. Seems weird to say the greatest one is minus 12 root 2, so I don't. Greatest acceleration is 12 root 2. You've got to remember, acceleration is that weird one where it's both a scalar and a vector. Because velocity, we have velocity and speed. Displacement, we have displacement and distance. Acceleration, we have acceleration and acceleration. So which one are we talking about? Let's look at some HSC ones. Oh, this is a little bit more interesting. Displacement is 5 plus 6 cos 2t plus 8 sine 2t, where x is the displacement in meters and so on. Prove that it's in simple harmonic motion. Well, sure, I can differentiate that twice. I can do it easier. But they've also given me the hint by showing that acceleration is minus n squared outside of x minus c. So when you have to show simple harmonic motion, minus n squared x, sure. But if you've got some shift happening, that's fine as well. X minus something. Okay, so let's look at this 6 cos 2t plus 8 sine 2t. We can turn that into one trig function. Now, that's going to be an easier way to solve this problem, because once I know the trig function, I can straight away look at it and say, oh, here's my amplitude, here's my thing. When I got it as two things, it's not as immediately obvious what it's going to be. So I'm going to turn that into one trig function using our auxiliary angle idea. So 6 and 8, hypotenuse is 10, the angle is inverse tan of 3/4, make sure you're in radians. So we get 10 sine 2t plus alpha. Remember, whenever you're using calculus and trig, radians for it to work. Got to be radians. So 5 plus 10 sine. Now I got a better picture of what this particle is doing. It's a sine curve. Yep, we got a shift happening. We also shifted up as well as far as displacement goes. Now I'll differentiate it twice, and I can show that, yeah, that's minus 4 outside of x minus 5. So it's in the form minus n squared x. Yes, there's a shift happening, but it is in that form of minus n squared x. When is the displacement of the particle 0 for the first time? Right, so we're saying, when is that equal to 0? Well, we'll just solve the trig equation. So sine 2t plus alpha is minus a half. 2t plus alpha is, now, yeah, sure, there's all these quadrants, but I want the first time. So I want the third quadrant answer, wouldn't I? That's the first time sine's going to be negative. So 7 pi on 6. Subtract my alpha and divide everything by 2, and I get 1.5. Just got to be careful with these ones where you're subtracting the shift. In this case, I was okay because I can't subtract from the third quadrant and get an answer that's going to go negative, if you get what I mean. So it must be the right one. But just be careful, because if your first answer you subtract and you end up with negative time, then maybe it's actually the second answer you wanted to get it back to positive time, if that makes sense. So after 1.5 seconds, just a little diagram here, some obvious things. Well, maybe it's not obvious, but at the amplitude, velocity is 0 because that's where it's stopping. So that also has to be where acceleration is a maximum, so out at the endpoints. Whereas at the centre, that's where velocity is going to be the maximum and acceleration will be 0. All right, 2020, so the new course, they finally put simple harmonic motion into extension 2. What sort of things do they now ask? A particle undergoing simple harmonic motion, the period is pi/3. The centre of the motion is not at the origin, it's at x equals √3. And when t equals 0, it has its maximum displacement, so it's starting at the end point, of 2√3 from the central point of the motion. Now make sure you read these things carefully. So it's not actually at 2√3, it's at 2√3 from the centre. Find an equation for the displacement. Well, I'm going to draw a picture for something like this to try and get my head around it. There's the origin, but it's not starting there. It's starting at √3. We said the amplitude was 2√3, basically, because the maximum displacement is 2√3. Therefore, it's going to go out to 3√3, but to the left-hand side, it's going to negative √3. Now, the particle starts at the amplitude. I know it's going to be in this form. It's going to be a cosine curve. So x will equal a cos nt, but plus some constant, because we've shifted the curve up or down an amount. We're not starting at the centre. The period I will now work out. Well, sorry, they told me the period. I can now work out n from that. So n is 6. So I've got n. The constant is my shift. I've shifted it √3. Now I know it looks weird that I'm shifting it horizontally, yet I'm adding a plus c rather than inside with it, but that's because x here is like the y value in a normal curve. So the shift's happening with the x, so it's a plus a constant here. So c is √3, and 2√3 is the amplitude. Bang, there's an equation. So find an equation, I've done that. X is 2√3 cos 6t plus √3. The next year, what did they do? So object, simple harmonic motion, of course, along our x-axis. We love travelling along the x-axis. Acceleration is -4, x -3. Again, we've got some sort of shift happening here, where x is a displacement from the origin, meters, seconds. Initially, we're 5.5 meters to the right of the origin and moving towards the origin. And the object has a speed of 8 meters per second as it passes through the origin. It'll be plus or minus, because sometimes it'll be going one way, sometimes it'll be going the other way. And that's why they've said speed rather than velocity. Where is it oscillating, basically, they're asking. So between what 2 points? Okay. They've given me the acceleration equation. So v to v dx, separate my variables. They've given me the initial conditions, displacement 0, velocity 8. Integrate, substitute in, I get my v squared equation, but I know that has to be greater than or equal to 0. Solving my quadratic, there we go. I get in between -2 and 8. So x is in between -2 and 8. Find the first value for which x is equal to 0. So when is it first going through the origin? 2 decimal places they want it to. You're allowed to use your reference sheet. They've got formulas on there. So one of the formulas is on there that simple harmonic motion can be in this form, not just minus n squared x, but minus n squared x minus a constant. So I know that. From the information we've worked out already, we know that n is 2 and my constant c, the shift, is 3. Also on the reference sheet, it tells me that if acceleration is that, displacement is a cos nt plus alpha plus a constant. We worked out the amplitude was 5. So I can now sub in, I've got 5 cos 2t plus alpha plus 3. Well, when t equals 0, x is 11 on 2. Where did we get that information from? Initially the object is 5.5 metres to the right of the origin. So I now know 11 on 2, I can work out alpha. Alpha is pi on 3. Alright, we want to know when displacement is equal to 0. We now have a trig equation to solve to find t. Eventually, I've got 2t plus pi on 3 is 2.214. This is cosine being negative. So I've got the second quadrant would be the first time. Be careful, we're dealing with radians, so 2.214. Do the subtraction, we end up with 0.58 to 2 decimal places, they said. Last year's one, much more fun. Look at this one. We've got 2 pistons. It's 1 piston. We have a piston but in 2 positions. The piston moves vertically in simple harmonic motion. We know the maximum height of 0.17 metres and a minimum height of 0.05. So it's going up and down like so. The mass of the piston they've given us is 0.8 kilograms and the piston completes 40 cycles per second. What is the resultant force on the piston in newtons that produces the maximum acceleration of the piston? Now, this is why it's in Extension 2. You'd never have seen a question like this in Extension 1 when it was in the Extension 1 course. This is where we have some fun. Alright, going to draw a picture to try and get my head around this. 0.17 it goes up to, that's the highest it goes up to. They told me the minimum 0.05. Well, therefore, 0.12 it's travelling. That means the centre of the motion is there, and I have 0.06 either side. So I now know the amplitude of my motion, 0.06. Okay, but that's been shifted up to 0.11. That's where the centre is, because if I take the 0.06 away from 0.17, now I know where the centre of the motion is. So centre of the motion is going to be at x equals 0.11. Frequency, they told me, was 40 cycles per second. But frequency is the reciprocal of period, so I now know period is 1 on 40. That allows me to find n. So n becomes 80 pi. There's my equation. It can be modelled by acceleration is minus 6,400 pi squared, n squared, x minus my shift 0.11. Maximum acceleration occurs at the amplitude, we know that. So it's either going to be 0.05 or what was my other option? 0.17. I used 0.05. Why did I use 0.05? Because I wanted a positive number. I mean, if I used the other one, I would have got negative, I suppose. So 384 pi squared. But the force is what they've asked me to find, and force is mass times acceleration, and they told me the mass was 0.8. Subbing that all in, I have my force. 3,032 newtons will produce the maximum acceleration of our piston. Okay. 6b and 6c, you'll find in 6b, these are questions where you tend to start with the trig and then go and prove it's simple harmonic motion, or you're told it's simple harmonic motion, whereas 6c goes the other way. You start with the acceleration and create the other equation.